Awesome. Dankeschön, Herr Kommandant, for that warm introduction.
You're welcome.
Fantastic. As a good friend and very wise man just said, this right now is my favorite moment of the favorite day of the year. It is the morning of GraphConnect. I guess that's the Swedified American way of saying it. I guess the localized British version is that it can only go downhill from here. That's another way of looking at it. But I choose to be Swedified American and say that this is the best moment of the day of the year. Cool. My name is Emil Eifrem, and I'm one of the co-founders of Neo4j and the CEO of the company behind the product and the community. And welcome to GraphConnect. I only have one ground rule for all my talks, and it is that I do not want your undivided attention. What I want you to do is I want you to test out the QE2 Wi-Fi by tweeting and Facebooking and Instagramming and Snapchatting or whatever you want to do. But let us know how we're doing. Give us feedback. Let us know if we're doing good or bad. The only thing that I ask of you is that you use one of the two hashtags. The hashtag GraphConnect is going to be monitored and pulled out on monitors, etc. And we always religiously follow the Neo4j hashtag. So we've been doing this for a while now, and I usually have this kind of, well, I used to for a couple of years have this silly kickoff kind of morning gymnastics routine, right? And don't worry, I'm not going to have you hug your neighbors or anything weird like that. Then for a while I figured, I can't have the same routine at every GraphConnect, and we're graph people. We want to change. We like change because it's so easy to adopt to it, right, and evolve with it with a flexible model. So I figured let's change things around. But then actually, so 2 GraphConnects ago, I started getting complaints about that. It's like, oh, you didn't have a stand up, the way we used to. And then actually at the last GraphConnect, I started getting angry tweets like, what the hell? You didn't have a... So, backed by popular demand, I want all of you who were at the first GraphConnect, everyone who was here at GraphConnect London in 2012, please stand up and remain standing. There was no GraphConnect 2012 in London. Walked right into that one, didn't you? All right. There was one in 2013, so anyone who was here in 2013, please stand up and remain standing. You don't dare to do it now, but there really was one in 13. All right, awesome. Anyone who was here in 14, please stand up. Anyone and remain standing. Anyone who was here in 15, please stand up and remain standing. This should be half, I guess, depending on the last comment that Lars did. And then anyone who was here in, did I say 15? In 16, please stand up and remain standing. And then, of course, anyone who was at GraphConnect in 2017, please stand up and remain standing. And give yourself a very warm welcome applause. All right, morning gymnastics is optional. You can now sit down if you so choose. Cool, we have a super exciting day ahead of us. We're going to start a little bit by taking a step back and talk a little bit about the past, a lot about the present, and a little bit about the future of Neo4j and graph databases. It's been a year since we were last here at QE2, and it's been a quite impactful and eventful year in the world of graphs. And I'm going to start out with giving you 3 examples of that. And the first example is probably a story that all of you have heard, the Panama Papers, right? It was one of the biggest news stories of 2016. In fact, it was the biggest news story of 2016 until Brexit. Thank you guys very much for that. And then I guess until the US election, right? So it was, 2016 was a big year, let's say, eventful year. In this particular story, the heroes are 2 German journalists who work at the Süddeutsche Zeitung out of Munich. And they got 2.6 terabytes of leaked data from a law firm in Panama which supposedly contained details about a lot of individuals who had registered offshore bank accounts in tax havens, which could be for legal tax planning purposes, but supposedly could also be for illegal tax evasion purposes. So you got this 2.6 terabytes, huge data dump of spaghetti information, and they wanted to make sense of that. They ran it through an amazing pipeline, open source pipeline, and OCR, all kinds of things, and ended up with 11.5 million documents, which, by the way, is the largest leak in journalistic history. 11.5 million documents. And we're talking scanned bank forms, government forms, emails, those kind of things, right? So a lot of stuff. And what they had to do then was make sense of all that, right? They ended up contacting an organization called the ICIJ, the International Consortium of Investigative Journalists, who'd gotten a reputation for being able to handle massive data leaks like this one from an investigative journalism and a data journalism perspective. Taking a step back away from technology, which we'll spend all of the day in the world of technology, but just thinking about investigative journalism, really what you're doing when you're an investigative journalist is that you're trying to find patterns, right? So here's an example of a pattern. We have a person. That person has an account with a bank, right? Not a very exciting pattern. That's true for me and for you and for all of us in this particular room, right? Here's another pattern. Let's say that person lives at an address. Another person is also registered to live at that address. This person is an officer of a company which is registered with a bank in the Bahamas. And all of a sudden, this is a much more interesting pattern, right? Because we can see that this individual here is now connected, not directly, but indirectly, to this offshore tax haven bank account. If we zoom out a little bit and look at this a little bit more abstracted, we can see that we had circles and arrows here, right? But these are actually concepts, right? We had persons, and we had accounts, and we had addresses, and companies, and things like that. In the graph world, we call these circles, we call them nodes, and we call the relationships, the connections between them, exactly that, relationships, right? And it turns out with these very simple abstractions, the building blocks of nodes and relationships, and then key value properties that you can attach to both the nodes and the relationships, for example, first name Emil, right? Last name Eifrem, and on the relationship, maybe, I've had this bank account since this particular date, right? With those simple building blocks, you can model everything, right? It turns out that this model is very flexible. It allows you to very easily evolve when business requirements change. Let's say that we start out over here with, looks like a social network or person to person, right, or something like that. And then after a while, we realize that, hey, actually, we want to be able to store companies, right, or bank accounts or something like that. There's no need to do a third normal form, refactoring or whatever. You can just add a new relationship with a new type. And your data model will organically evolve with you as business requirements change. That's what I call a compile time advantage. It's an advantage when you sit down and you build your system, right? What's even more amazing, or at least equally amazing, is when you wrap this in an infrastructure that can handle not just 1, 2, 3, 4, 5, 7 nodes, but it can handle 1 million nodes, or 11.5 million nodes, or 1 billion nodes, or hundreds of billions of nodes. And you can get to truly massive scale. And that's really when things start to become very, very interesting. Getting back to our story, that was actually not a theoretical example. If you look at the actual, how that played out in the Panama Papers, this was the example of the Icelandic prime minister, who was not directly connected to an offshore bank account, but he lived at an address where someone else, who subsequently turned out to be his wife, was registered with the company who had this bank account. And I actually misspoke. He's no longer the Icelandic prime minister. He had to resign thanks to the findings, or due to the findings in the Panama Papers. That's the type of impact that you can get when you put your data in a technology where you can see not just the things that are directly related, but also indirectly related. This ended up, as I mentioned, being one of the biggest stories of 2016. It had stories in every major newspaper in every country in the world. And we were super excited last month when the Panama Papers investigation actually won the Pulitzer Prize, which of course is the most prestigious prize in all of journalism for the Panama Papers investigation. Pretty amazing. So reflecting on this a little bit, what's been going on here, right? So what's interesting about this, there's so many things that are interesting about this story, right? But one of the most astounding things in my mind is that 5 years ago, this would not have been possible, right? So the documents that were leaked, they dated all the way back to the 70s. So this leak could have happened 5 years or 10 years ago, right? But 5 or 10 years ago, there was not a single organization that could make sense of this size of data set, right? Outside of the Googles and the Facebooks of the world, and quite possibly the big government, the NSAs, et cetera, of the world, right? Now the ICIJ seems like it's a massive organization because of the impact that it has, but it's basically a small startup. There are 12, 15 people out of Washington, D.C. They have 3 developers, right? But thanks to this open source platform that is emerging, of which Neo4j plays, I hope, a central part, like 3 developers could make sense of the biggest data leak in journalistic history. And that, I think, is quite astounding. On a separate but related note, Neo4j, the company, not the product, but Neo4j, the company, we think of ourselves as a mission-driven company. Our mission is to help the world to make sense of data, We're big believers in strange things like facts and data to back decision-making. And 2016 was a pretty stark reminder that facts and data is sometimes missing in the world of news. We've all heard the discussions around alternative facts, which is something that rubs me personally extremely. I have a very hard time adjusting to the fact that a lot of people react to make very important decisions based on what's proven to be false information, right? We think we can play a small role in this. I think the Panama Papers was one example of that. We're now going to launch another example of that. And so today we are announcing the Connected Data Fellowship Award, which I am super excited about, and in particular talk to all of you about, because maybe one of you feel like this whole issue around fake news is interesting and important, and then I urge you to apply. So what it is that it's a 6-month sponsorship for a data journalist, which is basically someone who's interested in uncovering stories and telling stories with data, right? To work alongside the award-winning ICIJ team, right? So work alongside with ICIJ for 6 months to help them to hold public and private institutions accountable. If you think this sounds interesting, go to neo4j.com/datafellowship. It will redirect you to ICIJ's website, and there's a link for you to apply. And then you can do your part in helping the world to make sense of news data. So that's my first story. My second story is in a completely different field. It's the world of medicine, right? So we do a lot of work in trying to help and enable the search for the cure for cancer. And when you look at something as complex as cancer, there's a lot of moving parts involved. There's a lot of factors, right? There's the particular samples and the compounds that you've selected in the lab. There's for a particular patient, there's their genetic makeup, there's their lifestyle, the diet, all kinds of factors that, of course, are related. They affect each other, right? And they are connected and influence each other, right? And that's a highly connected world. The challenge is that if you look at any healthcare company on the planet today, they have data that is stored in legacy technologies that aren't good at managing connections, right? And in completely disparate silos. So you have this highly connected problem domain where much of the understanding comes from figuring out how this thing is related to that thing, but your data sets are trapped in these silos, which are poor in and of themselves at working with connections, and they're disconnected across themselves, right? So what if you could take a world like this and you could take all this data and put it in a graph database, and all of a sudden you can see all these connections, right? And then you can see that this particular compound on this specific segment of the population with this food diet is reacting in a particular way. And all of a sudden, researchers and doctors can see cause and effect, right? Kind of the butterfly effect. If I change something over here, it'll cascade through everything and change something over here. I don't think I need to talk about kind of the value of the cure for cancer. Unfortunately, I think probably every single person in this room, if you go one hop out in your graph, or at most 2 hops out in your graph, you're going to have someone who's been impacted by cancer. I personally lost a family member to cancer. And I think that's true unfortunately, for a lot of people. And nothing makes me more proud than the work that we do today. There's 8 independent research projects that I know of that are using Neo4j to accelerate the search for the cure for cancer. So that's the second story. The third story is completely different from the first and the second story, and it takes place in space. So for that, let's move north from Panama and go to Houston, Texas, and to the Johnson Space Center, which of course is the headquarters of NASA. It's also the base of operation for Project Orion. And Project Orion is the mission to send mankind to Mars, right? It's a very, very cool, from an engineering perspective, an amazingly cool story. But not long ago, the engineering team of Project Orion had a huge problem. And the problem was that in all of their tests and simulations, when they saw the return capsule get back to Earth and splash into the water, it ended up tilted. And there's a part of the capsule that is called the uprighting system, which does exactly what it sounds like. It takes the capsule and it tilts it back up. And that's a good thing because this thing is carrying 4 astronauts. So we want it to not be tilted and sink. That's a bad thing. And so what's interesting about this, of course, is that this is not NASA's first rodeo, right? They've sent equipment and people into space for half a century now, right? And what's even more interesting is that NASA is, I don't know, maybe the premium engineering organization in the world or something like that, rivaled maybe only by the Neo4j engineering team. And they've been incredibly disciplined over the course of 50 years to record their successes and the mistakes in what they called a lessons learned database, which spans half a century of institutional knowledge for NASA, right? Dating all the way back to the legendary Apollo missions, right? Super cool. It's actually good specifically about the Apollo missions because it turns out that the uprighting construction on the Orion is the same one as the one on Apollo. So when the engineering team ran into these problems with uprighting the capsule, they said, hey, maybe they ran into the same problems in Apollo. Let's look at our database, right? So you have this massive database, but of course, it's of no use if you can't find anything. They searched, and they couldn't find anything in their lessons learned database. They even went to NASA's history office, and who spent 8 days looking through all of their old files. They found 3 files, neither of which was relevant. So out of pure desperation, they went and they found all of the retired astronauts from the Apollo mission who were still alive, went to their homes and looked in their attics to try to find something that could be related to this. But nothing turned up. Our heroes in this case, of course, is a small team who found a graph database. So there's a small team under the supervision of NASA's Chief Knowledge Officer, and maybe one day I could become something as cool as the Chief Knowledge Officer of NASA. David Meza, who basically said, all right, so we've had the lessons learned database in this format that is good for putting data in, but not really good for finding data. Let's build a project where we take this data and we move it over into this graph format instead, right? They did that, took a while to build the system. Once they launched it, in 3 hours, they had found 30 potential hits. In the top 10 hits was the solution to the uprighting problem on Project Orion. So the mission was back on track. And afterwards, one of the engineers on the Orion came up and he talked to David Meza, the chief knowledge architect. And he told them that if they hadn't found this is their absolute last resort, the next step after this would have been to build a completely new upwriting construct, which would have taken 2 years and cost millions of dollars. Neo4j, as probably everyone in this room knows by now, is a graph database, right? And that's good, but it's actually much more than just the bits and the bytes that we produce, right? Really, what Neo4j is the entire ecosystem around Neo4j. The graph-aware frameworks, all the drivers that people are building for languages that we don't have time to support, all the integrations with various frameworks, all of the community activity, really everyone in this room. So you can think to yourself, right, as you sit here right now, you're all part of this community. We're building this thing together. So everyone in this room, you contributed to making sure that mankind will get to Mars 2 years earlier than before. And I think that deserves an applause. Cool. So those are 3 stories. So what's the commonality here, right? What's the common thread, right? So really the common thread here is that people were held back by their existing data technology, right? And there's a lot of databases out there and a lot of really good databases out there. I've been on the record many times saying that I was and I remain a fan of the relational database. I think the relational database is one of the best pieces of computer science invention and engineering out there. I think it's a fantastic piece of technology. But not just that, there's a lot of really good non-relational databases out there. There's a lot of good document databases and key value stores. And they're all performance, and they're scalable, and they're robust, and like all kinds of amazing things. One big problem that I have, though, with all of these is that fundamentally, I think they have a simplistic approach to how they think about data, right? They have what I call the store-retrieve approach. You take data, you write that data into the database. Later on, you retrieve exactly that data back out, right? It's store that data, it's retrieve. Yes, fancy schmancy, eventual consistency, scale out, performance, robustness, whatever, right? But like fundamentally, that's what they do. With a graph database, you can do much more. With a graph database, every time you write data, you enrich the entire graph because you take that piece of data and you connect it to the rest of the world. So when you then read it out, you're going to get back context. You're going to get back everything that you can get back everything that it's connected to in one depth or multiple depths, right? So you write some data back, and what you get back out is much richer, right? And in that context is things like potentially fraudulent prime minister, right? Or the solution to the mission to Mars, right? Or the cure for cancer, or in that context is the basis for your real-time recommendations or your fraud detection algorithms or the backend to your machine learning systems, right? We call these actionable insights, and it's a completely different philosophy in how we look and a different level of ambition in terms of what we want to give to you as end users of a database. Cool, let's switch gears completely. Talk a little bit about broader adoption of Neo4j. So for those of you who stood up fraudulently when I said 2012, which was not, we weren't here in 2012, but in 13 and 14 and 15, you've probably seen this slide a lot. So back in, actually it was in 2014, Forrester Research, one of the leading analyst firms in the world, they made a very bold prediction. They said that 25%, over 25% of enterprises will be using graph databases by 2017. I must have been on stage, I don't know, 500 times probably, reading this exact quote, right? It's a great quote, very aspirational. I started preparing this presentation, and I put up this quote, because it's a great quote. But then I realized, wait, 2017 is now. It's this year, right? So I thought now is a good time to kind of reflect. Let's look at the scorecard. How are we doing, right? How good was Forrester at predicting, right? 25% of the world's enterprises. So when we look at Neo4j today, just Neo4j adoption, they talk about graph databases broadly, but just specifically in Neo4j, we can look at a couple of snapshots in a couple of industries. The first industry is retail. As of today, 7 of the top 10 retailers in the world are using Neo4j. 7 of the 10 largest retailers in the world. Almost half of the top financial services firms are using Neo4j. And 80% of the top 10 software vendors are using Neo4j today. I thought that was pretty mind-blowing. So the question then is, what are all these big companies using Neo4j for, right? And so we've identified 6 top use cases, which are the most common use cases out there in the enterprise today. The first one is real-time recommendations. So this is, rather than taking a structured tabular view of your purchase history, you take that data, you extract it into a graph, all of a sudden you can see patterns and you can do recommendations based on that. Customers like Walmart are doing that today. Second use case is fraud detection, right? It used to be that with fraud detection, if you just looked at individual points, you'd be able to do anomaly detection, right, in investigation. Now, fraudsters are much more sophisticated. They typically work in groups, right? Or they do individual transactions that in and of themselves are completely okay, but as a pattern, they become fraudulent. Whenever stuff like that appears, a graph database has ended up being a very good fit for fraud detection. Many of the big banks today are using Neo4j for this. Network and IT operations, if you're a big telco, that's all about, like your entire business is about managing networks. Well, what if you could have a model of your entire telco network, and so that you can figure out that if this cell tower over there blows down, how will that cascade across my network? Or if you manage a data center, what if my firewall goes down? What happens? Or if I have a breach over here, how could that cascade across my architecture? Right? So HP is an example of a customer that has a product in this space. Master data management has a lot of aspects to it. One of the aspects is storing hierarchies, making sure that all of your organizational data is correct, or all of your product hierarchy data is correct. It's a very common use case for master data management. Cisco was our first ever Fortune 500 customer back in 2011 doing master data management. Graph-based search is kind of related to the Google perspective, where they took a graph perspective on web search, and through that were able to just make search a lot more powerful. And we have a lot of customers using graph databases for exactly that. And then finally, identity and access management, which is, let's look at your big organization, take all your individuals, look at how they belong to groups. Sometimes groups belong to groups. Those groups have read and write permission to certain assets and collateral. This use case is also called entitlements in the financial services industry. These are top use cases that we see, but fundamentally, graph is a horizontal phenomena, right? This notion of making sense of data through figuring out connections is not confined to particular use cases or particular industries. These, however, seem to be early adopters inside of the enterprise. So that's the enterprise. It's a very important segment to us. Equally important is startups, right? So I, of course, have a particular love, since we're a startup ourselves. We have a startup program where you can get Neo4j Enterprise completely for free, or at a significantly reduced price, depending on how many employees you have. This startup program, we launched it, I think, 18 months ago. And today, we have over 470 startups in that program, right? Which I think is pretty amazing. You may not recognize all of the logos on this slide, or in fact, you may not recognize any one of the logos on this slide. But I bet that between these 470 startups, there's going to be at least one startup who's going to end up being a household name over the next 10 years, based on their ability to work with connections in data. So the question then is, okay, so what is driving this shift, right? What is causing all these companies, startups and enterprises, to adopt Neo4j? And really, it's the search for a competitive advantage, right? It's sometimes solving an actual business problem on the cost side, but much more frequently, it's about finding a competitive advantage. And of course, one way of looking at this is to take a case study. And the most dramatic one that I know of, when people have taken their data and they've connected it in order to win in their industry, is in the consumer web, right? For those of you who are around in the late 90s, I'm not going to have you stand up, but for those of you who were around in the late 90s professionally, you remember that there were like a bunch of search engines, Lycos and Alta Vista and Excite and whatever they were all called, right? And they all did exactly the same thing. They downloaded the entire web. They put it in their data center. When you search, you looked inside each and every one of these documents. You search for QE2, right? And then every document that has that, I'm going to serve that back up to the user, right? And then along comes a small startup which said, this is awesome. I'm going to do that, exactly that. But on top of that, I'm going to look inside of these documents. I'm going to find the links. I'm going to build up a graph of everything that links to everything. I'm going to rank the search results based on that graph, right? And of course, the name of that algorithm was PageRank, and the name of that tiny little startup was Google, right? And they ended up completely dominating this industry based on that shift in perspective, where they said that data in isolation is very valuable, but connections between data points are also valuable. So let's use that and reimagine our industry along those connections. Another example is job search, where there's been a lot of job sites for a long time. And then LinkedIn came along and said, we're going to do exactly what you guys do, except we're also going to get people to volunteer their professional connections, which is why Monster.com is, I don't know, $400 or $500 million company, and LinkedIn ended up being, I think, a $26 billion company, right? And another example of this, also from the late 90s, early 2000s, is PayPal, right? There's a lot of people who try to do online transactions. The key challenge with that is fraud. And it turns out when PayPal had a network view of all the transactions, it's a lot easier to detect fraud, which is what I previously talked about when we talked about fraud detection, right? These are 3 examples of companies that went in and they took their industry and they reimagined it based on connections. And that allowed them to win and dominate their industry and become hugely valuable companies, right? So basically, it was built on two things, right? First off, there were connections in data, right? But also their ability to leverage those connections. If we translate that to your world, the first component, connections in data, is just a function of time. As data grows more and more, as the world is becoming increasingly connected, data is just becoming more and more connected. This is going to happen thanks to the inertia or due to the inertia in your industry. So really what ability you have to influence this is the second one. How can I use those connections? And that comes down to a technology choice, right? Choosing a platform that is good at managing these connections. So let's look at some popular examples. Of course, the vast majority of databases in use today, of course, is the relational database, which, again, is a fantastic piece of innovation. It's good at a lot of things. One thing that it isn't good at, however, is managing connections in data, because that leads to a lot of joins, which ends up with a huge performance problem at even trivial sizes, even tens of thousands or hundreds of thousands of rows. If you want to do 2, 3, 4, 5 hops, you can't do that, at least not in real time. Another kind of popular technology is the entire kind of big data landscape with the Hadoops and the data warehouses of the world, which are also amazing and good for many things: analytics, BI, MapReduce style operations, right? What it isn't good for is operational use cases, transactional stuff, right? Or for that matter, fast queries, right? So a fast query in a data warehouse may be minutes, maybe seconds, right? But sometimes it's hours and days before you get your reports, right? So wrapping up then, getting back to, we've talked about the Forrester quote, the 25%, right? We talked about the traction in enterprise, the traction in startups. We've talked about the value of being able to use connections in data, and that has unlocked a lot of market cap for some really big companies in the consumer web. So reflecting then on this and then looking at all of the data that we have internally around our traction, I want to think about the Forrester quote again. So they said 25% or more by 2017. And the conclusion, when we look at all the companies that are either using Neo4j, open source or commercial, or piloting with Neo4j today, actually over 50% of the global 2,000 are now using or piloting Neo4j. So it turns out, thank you. So it turns out that the Forrester analysts were conservative, which is interesting to see. Cool. So at the center of all this, of course, is the amazing community around Neo4j. And at the center of that community, of course, is the product. So I'd like to introduce up on the stage a very important individual, none other than my colleague, Philip Rafley, who is the head of product for Neo4j, and is going to tell you some amazing things about the present and future of Neo4j. Philip Rafley, take the stage.
Thanks, Emil. All right, before we talk about product, I'd like to talk about an important initiative that's been taking place inside of the Graph community, and that's OpenCipher. And OpenCipher is an initiative based around the Cypher query language, which, as most of you probably know, is a query language that's designed and optimized specifically for conveniently writing to graphs and reading from graphs. And a dedicated query language is the natural conclusion that emerges if you believe that for different kinds of problems involving discrete data or connected data, that you can benefit from taking a different perspective around the data itself. And that different perspective can benefit from having different technologies optimized for handling those kinds of questions and queries. So natural conclusion from spending lots of time following this rabbit down the rabbit hole is that much like in the SQL space, we've discovered that having a query language dedicated for that model. In the graph space, it's also a great benefit to users in terms of productivity and power to have a dedicated language for querying graphs. Cypher's not our first attempt, nor our second. It's our third or fourth or fifth attempt at, over the history that Lars and Emil have talked you through, at designing and building a graph query language. And Cypher's the one that really stuck. There are some unique things about Cypher that are really special. One is the reaction that people have when discovering Cypher for the first time. On any given day, you can go out to social media or join a local Neo4j training and see how people respond to this powerful way and simple way of querying graphs. And this also illustrates the power of open source, that through a community you can create this amazing feedback loop and improve a language so that over the last 5 years that Cypher's existed, 6 years now, it's become more robust, more applicable to real-world problems, and more suitable for user needs. One can also deduce that Cypher is the most used graph query language, and in fact, if you look at the time a few years ago when graph databases made a popularity breakout from all these other kinds of data technologies, the launch of Cypher actually coincided with the time that graph databases really took off from the pack. This is when Neo really started to grow. It's our belief that in order for this technology and this model to fulfill its promise, that it's important to have a high-quality open language. And this gives you as technologists a skills transferability as you go from different tools and databases to different vendors and so on, as well as giving IT the confidence of being able to, again, transfer skills, transfer data, and so on. So to that end, Cypher, of course, started as open source, but only as part of Neo4j. And 18 months ago, we made an announcement that we would make Cypher available to anyone under a more liberal license. And over the last few years, over the last 18 months, that initiative has been evolving and has morphed into actually an open process that's open to anyone and that's now governed by consensus. And all this is headed, of course, in the direction of there being a formal standard that all of this will morph into. Some of the resources that have been developed during this time include lots of documentation around Cypher, a technology compatibility kit so that you can test whether your particular implementation of Cypher is correct, as well as a grammar from which can be derived parsers. A number of databases now support Cypher. Today there are 6, including Neo4j and including databases like SAP HANA. And there are a number of tools in a growing ecosystem of products that support Cypher. Cypher's evolved over the years and has continued to evolve. And there are a number of specific next steps that are planned for this year. 2 of the important ones are evolving the language so that you can query a graph from Cypher, that's already possible, but return a graph so that you can have a full closed loop for use in views or passing Cypher query results to Cypher query results. Another one is integration with SQL. SQL and Cypher each have their place, and being able to have SQL queries call Cypher queries and vice versa can potentially be useful. Some of this is already possible in Neo4j through procedures, and the next step is to actually lift that functionality in as a first-class feature in the language. A little bit about the process so that you can maybe be inspired to get involved, which we would very much welcome, as would the other community members. There are currently, as of last night, 37 issues on GitHub under OpenCypher around improvement requests and proposals. These have been evolved through a set of meetings and offline processes. There have been 2 face-to-face meetings as well. The first one in February in Waldorf, Germany, and the second one just yesterday here in London. And in case you're looking for something to do this summer, there will be twice monthly calls to work through some of the issues and next challenges for the language that I mentioned. Those will be public Cypher language group meetings that anyone can chime into. So if you're interested, just chime into the Google group, start with opencypher.org, and you can find lots of links from there. All right, that's OpenCypher. Let's talk about Neo4j. Last December, we released a new significant release of Neo4j that we described as being the graph foundation for the connected enterprise. Neo4j made it really easy, much more convenient to deploy Neo4j across an entire enterprise for many different use cases in a way that conformed more readily with the kinds of IT standards around security and clustering and operability that IT departments expect. What we've been working on since then is a new release, Neo4j 3.2, that takes that data center view and that IT view and lifts it up one step towards a global data center view for internet scale applications. So really, there are 3 themes to 3.2, 3 parts to it. One, as I mentioned, is global scale, being able to run across multiple data centers around the globe. Another is taking yet some additional steps in governance and security. And thirdly, lots of improvements in performance across the entire stack. So let's talk about scale first. Let's go back to 3.1. In 3.1, we introduced causal clustering as a new form of clustering, a 3rd-generation clustering architecture. Some of the key features were it enabled ultra-high throughput with features like read replicas, so a part of the cluster that accepts writes and reads and a part that accepts writes. Guaranteed redundancy, higher guarantees than in prior architecture. All of this ACID, of course. Read your own writes through a choice of consistency levels, including causal consistency. Neo4j is one of the first databases to support this model, as well as built-in routing and a level of convenience around the routing that cuts across the entire stack. So the Bolt protocol that was introduced in 3.0, along with the drivers, work together with the cluster to provide a seamless and powerful set of clustering features. With 3.2, you can now take an entire cluster and have the cluster understand its topology to be able to configure a topology that matches up with the real-world topology of your infrastructure. Some of the key features here are more global multi-data center topologies, geo-aware load balancing, so having load that basically moves according to your configuration so as to minimize traffic across the WAN. Tiered replicas, so even inside of a data center, you can have tiering of how your data propagates inside of a cluster. And then finally, there have been some really significant improvements to the API that was launched in 3.1, making it very convenient to leverage all of these powerful features. Our goal is that you can write an application once for Neo4j. It'll work with Community Edition or Enterprise Edition. You can move to Enterprise Edition without having to rewrite anything. And then all of the infrastructure is just managed by the database. You set up the topology, and then you as an application developer don't have to worry about all these complex considerations that come into play when building distributed global applications. So that's something we're very proud of, and we look forward to you experimenting with and giving us feedback on. Next feature area is governance and security. And if I look at Neo4j 3.1, we introduced 3 things. LDAP and Active Directory support, users and roles, and procedure access controls. There are a few other things beyond that, but that broadly is the new security foundation that was created in 3.1. What we've been working on since then is building upon that. Many of you, especially in financial services, healthcare, and other security-sensitive organizations have told us that you absolutely must have Kerberos, so we've been working on that. Another is actually expanding the schema capabilities of Neo4j. If you're integrating Neo4j with other systems, you actually want the database to be able to enforce the schema constraints that you have in other systems. Node keys let you do that by guaranteeing existence and uniqueness across one or more properties. And then last but not least, another highly requested feature has been intercluster encryption. And I'm pleased to say that the first 2 are available in Neo4j 3.2, and the second is being worked on, and intercluster encryption will be coming soon. Then last but not least, let's drill into performance. Basically, every Neo4j release we've done for the last, I don't know how many years, has included some improvements to performance. And in 3.2, we took advantage of, all right, you get to see the rocket ship again. Double NASA. We've made performance across the entire stack. And this is one of the advantages that we have as a native graph vendor and owning all aspects of the stack. We can make changes in how the data is stored. We can make changes in how the data is transmitted over the protocol. And we can do all sorts of things in between with the query optimizer and how data is indexed and so on. In 3.2, we made a big improvement for write speeds that across the board should improve writes anywhere between 30 and 300% depending on your particular data set. And the way we do that is by introducing a new kind of indexing scheme for a type of index that probably most of you don't know exists, called a label scan index, that supports, that basically comes into play anytime you have any data that has labels. This makes things much faster. We've also introduced composite indexes. Many of you said it's great to be able to index one property so I can parachute into the graph efficiently. But if I have multiple properties, it's not that efficient to have multiple indexes. So now you can have a single compound index. This is available in both editions of the product. An important kind of query in Neo4j is to specify a certain level of depth and to match a pattern and return all the nodes that match that pattern for that level of depth. These kinds of queries, called reachability queries, are going to run much faster, and the larger the graph is and the deeper the query, the more improvement you'll see. And you can actually see for three plus levels of depth for anything with hundreds of thousands or even low single-digit millions of nodes or more, which is not that much data, orders of magnitude, an order of magnitude improvement. Another is we've been working for a couple years on a new runtime for Cypher that compiles the Cypher down to Java bytecode and then runs it. This is available initially in Neo4j Enterprise Edition. It's available for initially a set of queries that is fairly basic, but kinds of queries that I expect probably all of your application will have several of. It's probably 80% of the kinds of queries you'd run into in your first hour of training. Queries are sped, again, mileage varies according to the query, but roughly 300% is about the average that we've been seeing for those affected queries. And then last but not least, we've rewritten the Neo4j browser from the ground up. We did it for two reasons. One is so that we could evolve it faster to serve you to add more features. But secondly, the performance of the Neo4j browser has not been that great. It's been written in Angular. It's a little bit of an old infrastructure. So we rewrote it in something that's React-like, and it's much snappier, much better experience. While we were in the Neo4j browser, we figured we'd do you one small favor. And while we were at it, we said, what's something that everybody does? You know, the main purpose of the Neo4j browser is to write Cypher queries. So why don't we see what we can do to make it more convenient to write Cypher queries? So what we've done is created a brand new graph Cypher editor. It supports full syntax highlighting. You now have autocomplete for relationship types, labels, properties, variables, including procedure return variables. And you also have autocomplete for your Neo4j browser commands. So that's a small thing, but I hope it'll make your lives much more convenient. So that's all Neo4j 3.2, and I'm pleased to say that the engineering team came together with the fastest turnaround for a major release in the 5 years that I've been at Neo. It's been less than 5 months, and Neo4j 3.2 is available today. So just a big shout out to the engineering team, most of whom are in this room today for their really, really hard work in getting all these features out to you so that you can try them out. Thanks very much. Back to you, Emil.
Thanks. All right, settle down, down here. Well. Cool, all right. Neo4j 3.2, super exciting stuff. I want you all now to load test the QE2 Wi-Fi. Pull up your laptops, download Neo4j 3.2 right now, and see if the Wi-Fi can withstand the onslaught of the best database in the world landing on all your laptops. Cool. We're going to wrap up fairly soon, but before that, I'm going to take a little bit of time and talk about the future. I want to talk specifically about maybe the biggest trend in technology today, bar none. Maybe the biggest we're in this room that we're going to see in the next couple of decades, possibly. And it's that of the broader world of AI, right? It has many names: machine learning, deep learning, etc. But at the highest level, for many, many decades now, like since the advent of computers, really, we've used computers to automate tasks where we could easily express the rules and the algorithms, right, using imperative programming languages, right, from Fortran to COBOL to C to Java, etc. Right? Now, what's been happening with the past probably 4 or 5 years, in reality, is that we've been able to get this capability called machine learning, call it deep learning, to automate tasks where the rules and the algorithms are not as clear to describe, where we can have the system figure them out for us, right? That's a huge impact, and we've all read about that and automation and the impact of that. But I'm going to talk about 2 things that I find particularly interesting about this that I'm going to spend some time on today. And the first one is that machine learning is based on graphs. So this is a book that was recently promoted by O'Reilly's chief data scientist, Ben Lorica. He's a good friend, and he said that this is like the best intro to machine learning that you can find, right? And you won't see the details in here, they don't matter. But chapter number 2 is graph fundamentals. chapter number 2 in this fundamental book about machine learning is about graphs. And the subsequent chapters then describe all of the techniques and the algorithms for machine learning using graphs, right? So an entire underpinning of how to use machine learning is graphs. So that's the first one that I think is very interesting. The second thing is the rise of knowledge graphs. And knowledge graphs, many of you probably remember when Google announced their knowledge graph, right? Which is this little panel over here. When you search for something like Queen Elizabeth II, you're going to get a little panel which outlines facts about this particular individual. This is when they don't just do a text search, but they actually pull it out of a much more semantically enriched graph, which they call their knowledge graph, right? But quietly in the background, they've started using the same knowledge graph for other things. In particular, they've been using it to power their machine learning systems, right? And this is based on the observation that for machine learning, context drives meaning and precision. Context drives meaning and precision. And context, what context is really everything, context about me is everything related to me but not me, right? So for example, this is me, right? And I'm the father of Nomi and Leah, 2 daughters. And I live in America. And I'm married to Madeline. And I play the piano. And I watch a TV from the 80s. This is supposed to be The Matrix. I don't know if that's obvious. I was born in Sweden. And I drive a Tesla. That's fake news. I don't drive a Tesla, but I wish I drove a Tesla. And so this is all my context. This is what gives me color. This is what makes you understand me. The data on me is first name Emil, age 39, age 38, age 38. Sex, male, stuff like that, right? And that helps you understand me a little bit. But how I relate to the world is what truly makes you understand me. That's the context, right? So Google has now started using this knowledge graph completely horizontally across almost all of their AI-based systems. If you're a Google user, you very likely used their knowledge graph, at least this week. Google Photos, smart replies in your inbox, like all kinds of facilities. People talk about knowledge graphs as one of the central pillars of the future of machine learning. So in parallel, we've seen a very similar story happen with Neo4j. Knowledge graph is actually one of the most common use cases for Neo4j. We have folks like Cisco who write kind of standard enterprise applications that use Neo4j as a knowledge graph, right? NASA is a great example of a knowledge graph, right? They took their lessons learned database that we talked about before and they moved it over into a knowledge graph rather than a tabular representation, right? And in Cisco's case, it's used by applications, right? Standard Java enterprise applications type stuff. For NASA, it's used by knowledge workers. And I'm a little bit out on a whim, but I think that Airbnb is doing the exact same thing. But I haven't yet seen their talk, which is this afternoon, right? But I believe that they're also building out a knowledge graph, which is used by knowledge workers, so by human beings, right? So we've seen this. We have probably tens of, if not hundreds of deployments like this out in the world today. But we're also seeing exactly the same trend that Google, who started out using it kind of by either manually themselves, by human beings, or standard applications like the little search panel, right, that showed Queen Elizabeth II, right? But then started using it as a basis for machine learning. And we see the same trend happening right now. One example of this that I want to talk about is eBay. So eBay, I don't know, 6 months ago, something like that, last fall, they launched something that they call ShopBot. And ShopBot is a chat bot that helps you shop on eBay, right? So it's their approach to conversational commerce, right? So basically, you connect to it on Facebook Messenger, and you start telling it, hey, I'm looking for, what's the example, for a black Herschel bag for under $80. And then it'll chat back to you, okay, cool, should I look here or there? And it asks you qualifying questions, and then they serve up product examples for you to choose, right? You can also, if you're at a friend's, you can take a photo. Hey, these glasses look awesome. Like, can you find similar glasses for me? It'll, look at that using visual image recognition and machine learning and figure out, oh yeah, we have similar pictures, similar product to this picture, that kind of stuff. So how does this work behind the scene, right? Oh, I'm not going to do it justice. It's a very sophisticated system, but at a very high level, they use NLU, Natural Language Understanding Techniques, not NLP, NLU, to take this chat phrase and make sense of it, right? So they identify that, hey, there's an object in there, there's an intent. In this particular example, there's a shopping intent, right? And then there's attributes, there's colors, material, brand, and there's a cost, right? So they take that. After that, they map that to their knowledge graph. And the knowledge graph for eBay is this succinct graph expression of all the shopping behavior on eBay. So this is, once they've made sense of the chat message and figured out the object, the attributes, and the intent, right? Then they know that there's a bag that someone is looking for. They use the knowledge graph to say that, hey, okay, bag is here, right? But since they haven't said anything more than bag, well, the most likely, if you're on eBay, is just from probabilistically the most likely is that it's either men's backpack or a handbag. So the context expressed by this knowledge graph helps this machine learning system to make sense of the world. Right? If you think this looks cool, you can add it today. Actually, you can just try it out. Go to shop.ebay.com, and you can start Facebook chatting with it. And before you know it, you've bought a bunch of stuff on eBay. Right? So that's cool. But I think this is, what's interesting here, this is a global internet scale application that is using knowledge graphs in Neo4j to do their machine learning. And my prediction is that we're going to see a lot more of those applications going forward. Going forward, we can say a lot of things about the future, but one thing that is very clear is that it is highly connected, right? People are increasingly becoming connected. Devices are increasingly connected. The world is increasingly connected. It would be very naive of us to assume that data wouldn't follow a similar shape when everything else in the world is becoming more and more connected. Of course, data will follow that shape. And I want to kind of end on this note that I always do at GraphConnect and reflect back on where we were 15 years ago, right, when we first started thinking about using an alternative approach to storing data compared to the existing relational paradigm. And we looked around for inspiration, right? And again, there's a lot of good databases out there to look at, but we looked much more broadly. And after a while, we figured out that actually the best database in the universe that we were able to find out was this, right? The human brain. And how's the human brain shaped again? It's neurons connected to other neurons, right? Which creates a big network or a graph. And the human brain is amazing at going from particular pieces of information into insights to make sense of data, the actionable insights that we talked about before, which is exactly the ambition that we have to provide to you all with our database. Speaking of ambition, I want GraphConnect to be many things, right? But above and beyond everything, I want it to be a friendly and warm conference. We all in this room, there's one thing that unifies us all in this room, which is that we're all graph people, right? So the foundation of graphs is relationships. We're not document people. So don't go out there and be sad and lonely and tragic and isolated documents. Go out there and be graph people. I have only one homework for you for the entire day, which is to connect. Strike up a conversation with your fellow attendees. Ask, how did you like the keynote? Between Lars and Emil, who looked the most like Brad Pitt? Or what do you think of Neo4j, the feature set in Neo4j 3.2? Strike up conversations, form relationships, and above and beyond, have a fantastic conference. Thank you very much. Thanks. Have a fantastic day.